speaking today. I'll let him take it away.
Yeah, thanks a lot for invitation, and hi everyone. So let me share my screen and I'll start the talk. Okay. So so this is the name of the paper, the Lagrangian Correspondence on a Pillowcase. And before I start, I should say it's a joint work with Guillaume Casazes, Chris Harold, and Paul Kirk. And by the way, if there are any questions along the way, please interrupt me, or you could also write it into chat. I'll be monitoring the chat as well. So, so let me start first with some motivation. So there's an invariant of a knot called reduced singular instanton homology. It was constructed by Kruheimer and Mrovka, and basically, given a knot, for example, here I drew a trefoil, they add an earring to this knot, which is one small meridian, and then they kind of study singular connections on the complement of this meridian and a knot. And using this singular connections, they construct a homological invariant called singular instanton knot homology. Yeah, and it's connected to other versions of instanton homology. Let me maybe mention that they did it in order. So part of the application of this singular instanton homology is that quantum homology, there's a spectral sequence from quantum homology to singular instanton knot homology. But this talk is kind of just focuses internally on this invariant. And really what we'll be studying it is this invariant, but from representation theoretic viewpoint. So gauge theory is like a motivation for the constructions which we will follow. And so from a representation theoretic viewpoint, something that one might consider is a representation space, which you call SU2 traceless representation space. And what that means is that I'm taking a fundamental group of the complement of all these gadgets, so the knot K, the meridian E, and also the arc W between meridian and a knot. So I'm considering all these representations, and then I want to restrict to those which are traceless on the meridian of a knot. So for example, this is a meridian of a knot. And I want to say that my representation has to be zero, trace of the representation has to be zero on that meridian, and it also has to be zero on this meridian. And that's why we're calling them traces, because and then there's one more condition which I want to throw in. This is the W2 condition. Basically the SO3 bundle in singular connections is kind of dual to this arc W, and so therefore on the representation space side, we need a condition that the meridian of this arc, so this is the meridian, its trace has to be actually -1. Well, actually not the trace, but the whole, the element in SU2. So yeah, to summarize, I'm considering representations from the complement of all this such that the traces on these meridians are 0, whereas this meridian actually goes to -1 in SU2. And this is what I will denote by R, and then natural at the top. And this natural represents the fact that I added an earring here. So this gadget is called an earring. Okay, and then I want to also consider it up to conjugation. Okay, so that's a representation space one may consider. Turns out that this representation space doesn't have to be like smooth or even zero dimensional. It can be higher dimensional. But the point is that then what we can do is also holonomy perturb it. And I don't want to say what are these, because I will say what are these later. So this is this pi will represent the fact that I consider holonomy perturb representations. And so once you perturb, turns out that this becomes a bunch of points. The key fact is that the complex, the singular instanton complex, is generated by the points in the holonomy perturbed traceless character variety. And so, yeah, so that's kind of the setup. But then, of course, we want the instanton homology, not just the chain complex generate, right? So the key question for today is how can we recover the differential on the instanton complex, which is the same as perturbed, holonomy perturbed SU2 traceless representation character variety. Okay, so how do I recover the differential? And kind of a classical idea in Floer, which goes under the name of idea-Floer conjecture, may be applied here. But let me say that actually it's rather hard to do it in this setting. And the reason is because if you kind of divide a knot along a sphere, which intersects the knot on two endpoints, and then one can consider traceless representation variety of this surface. It turns out it can be highly singular. So it's not really straightforward and clear what type of symplectic geometry one has to study on this space. But the good news is that if we consider Conway spheres, so spheres which intersect knots in 4 points, then this traceless representation space is not so bad. Okay, so that's the kind of the main idea. And so next I want to describe the Pillowcase homology construction. Okay, so the Pillowcase homology construction is a framework in which I will basically operate. So this framework is due to Haddon, Herold, and Kirk. And what they observed is, first, the traceless representation space associated to a sphere with 4 points is actually a torus modded out by elliptic convolution, which is the famous Pillowcase. Okay, it's a 2-sphere with 4 Z2 orbifold singularities. That's the first observation. And yeah, I mean, this space is still singular. It's not smooth because there are these 4 points, but one could remove these points and obtain a symplectic manifold, non-compact, but still. And actually, one can consider Lagrangian Floer theory in this space. It's, yeah, it's well defined. And so, as such, they proposed the following way to study singular instanton knot homology. So they proposed to cut the knot along a Conway sphere, intersecting the knot in 4 points. And so on one side, there's a tangle T1, and on the other side, there's a tangle T2. And so we want to associate to each of these tangles Lagrangian submanifolds, which means really curves inside the Pillowcase. And then there's kind of a general theorem which Herold and Kirk proved. And what they proved is that basically, if I consider representation space of, well, let's start with tangle 2, actually. So in this case, it's kind of complicated tangle, non-rational tangle, T2, what they observed is that if one takes this ball and a tangle inside, and if one considers traceless representations, so meaning the representations of a complement of this tangle, such that they are traceless on the meridians of this tangle. And then one perturbs, so again, one has to throw in enough holonomic perturbations. The output actually is a non-compact, immersed, smoothly immersed curve inside the pillowcase. So notice that on this tangle, I don't have an earring. Okay, and so yeah, in general, it's non-compact. In fact, it has to be, one of its component has to be non-compact. So that's the first observation. And the second observation is that if one throws an earring into one of the tangles, which means that now the traceless representation space will be also on the complement of these gadgets as well, with conditions of traceless being on this meridian and -1 on this meridian. So in this case, I will denote this traceless representation space by R natural, and pi indicates that I'm, again, holonomic perturbing it. And they proved that actually this space smooth is, first of all, smooth, and second, it's compact, and it actually immerses into the pillowcase. And so as such, the two tangles, they actually provide two curves. And I don't know, I'll just draw an example for an example curve. So for example,
Artem, can I ask a question really quickly?
Yeah.
Why not add an earring on both sides?
So that's definitely an option. But in order to match the singular instanton homology, we would need to add an earring only on one side, because in singular instanton homology, there was only one earring. We could put another earring here, but then would have two earrings. And, you know, there is a corresponding knot homology for that construction. It's just a little bit different. My guess is that it's probably
double the rank of singular.
Yeah, my guess is that it will double the rank. Yeah. Yeah, absolutely. And so, yeah, just as an example, for example, the curve which is non-compact could be this, and then the curve which is compact could be, I don't know, this. And then we would, well, okay, this cannot really be the case. Maybe it's, let me do this one. And then their suggestion is that the intersection Floer homology of these two curves, so HF will represent for us Lagrangian Floer homology of curves. So in this case, it's one-dimensional, for example, because there are no bygones. So their conjecture is that this Lagrangian Floer homology, which they name to be pillowcase homology, first of all, it makes sense inside the smooth part of the pillowcase because both are smooth curves. And yes, I mean, one has to worry about unobstructedness a little bit, but even with unobstructed, even with fishtails, one can cook up a easily well-defined group associated to these two smooth immersed curves. And their conjecture is that this pillowcase homology should recover instanton Floer homology. And let me give you immediately an example, just so that we can imagine this better. So for example, I can consider this decomposition of a trefoil. So there's this three-twist tangle on outside, and there's a trivial tangle inside with an earring. Okay, and it turns out that to such decomposition, to such a conway sphere, the representation theory, traceless representation functor associates, so the non-compact curve will be this. And yeah, I mean, now the pillowcase looks like this, but now I'm drawing my pillowcase, as if these are my four corners and my blackboard is the whole pillowcases. Okay, this is the way I'm going to draw these curves. And so the curve associated to this tangle is this one. Now the curve associated to this trivial tangle will be this curve if I don't add the A-ring. So it's non-compact. But remember that I need to add an E-ring to one of the curves. So if I add an E-ring to this curve, sorry, to this tangle, the resulting curve are natural. And then I'll have to perturb, actually, if I want to do this, will be this figure 8. Okay. And this is a computation, again, due to Hedden-Heralding.
May I ask, Artem?
Yeah.
If you were to sort of, move the earring to the other side, so how does that affect the picture then?
Yeah, this is the topic of the whole talk.
Okay.
So thanks for the question. Yeah.
But, go ahead.
Yeah, but running ahead a little bit, I'll just say that in that case, this curve will become a figure 8. Mm-hmm. And this curve will stay to be an arc. So in this particular example, but in general, what will happen is precisely the topic of this talk, and I'll tell you exactly.
Okay, thanks.
Mm-hmm. Absolutely, yeah. And so you see that the Floer homology of these two curves is 3-dimensional. This is the minimal intersection picture, and that is precisely instanton Floer homology of trefoil. Singular instanton Floer homology of trefoil. And let me say that this computation generalizes to 2 bridge knots. So the pillowcase homology recovers p-dimensional instanton homology of a KPQ 2 bridge knot. And also Hedden.
Artem, quick question. Yeah. This is not known to be well defined, though, is it?
Yeah, so that's not known to be well defined. Yes, you're absolutely right. This is just that's right. So only for trefoil it works. For 2 bridge knots it works. And so these are so let me address this on the next slide, basically. Yeah. I just want to say that there are many other supporting computations, so not only 2 bridge knot and some other torus knots as well, in which the computations actually work, and the result is instanton Floer homology. So now addressing Nikolai's question is that basically pillowcase homology is not known to be well defined because it's very hard to control how this Conway sphere is placed. Like you can have a knot place a Conway sphere here or here, and how do we know that we'll get the same pillowcase homology? There are some ideas for how to approach it, but in general, it's quite difficult to tackle this. And also, it's quite difficult to tackle the equality of pillowcase homology with instanton Floer homology. And in fact, we speculate that the construction of pillowcase homology has to be enhanced in order for this isomorph to really work. And at the end of the talk, I'll say what exactly enhancements we expect. So now I want to describe what the topic of this talk, and basically, each difficulty in both of this question is an open-ended research direction which one could pursue, and what we will explore is the phenomenon of dependence on the earring location. So exactly what Danny asked. So if I place an earring on this side versus placing an earring on this side, how does the intersection picture really change? Can we prove, for example, that Floer homology doesn't depend on the placing of an earring? So this was kind of the first question that we asked ourselves, and we have basically a satisfactory answer to this, which I would like to present. And in particular, I mean, embedded in this question, dependence on the ring, the key question is, okay, if I have a representation traceless representation for a tangle, what is the traceless representation for a tangle if I add a nearing, right? What does adding a nearing do to a representation variety? That's the main question. Okay, and the results that we'll get will give us insights into necessary upgrades of Pillowcase homology. So yeah, so this was kind of the motivational part. Are there any questions maybe? Okay, so continue. So in order to describe the effect of adding a nearing, I will need a concept of Lagrangian correspondence. And so Lagrangian correspondence is a object due to Weinstein. So it's something which can be defined for two symplectic manifolds, M omega and N omega. And it is actually an immersed Lagrangian L inside the product of M and N, okay? And also, I need to reverse the symplectic form on M, okay? So this becomes a symplectic manifold, and so Lagrangian submanifolds make sense inside this symplectic manifold. And the way I will describe, I will kind of draw this Lagrangian correspondence is by drawing the immersed Lagrangian and two projections, one on M and another on N. Okay, and two quick examples. So first, Lagrangian correspondence actually generalizes usual Lagrangians in the following way, that I can have a Lagrangian correspondence from a point to a manifold, and that's exactly, you know, there's one map to a point, so that's basically the same as Lagrangian inside symplectic manifold. Okay, so that's the first example. Second example, more interesting. If I have M and M, so two same symplectic manifolds, there is a diagonal, right? And diagonal actually gives a Lagrangian correspondence between M and M. Okay. And so the third example which I want to give is actually the reason why we care about Lagrangian correspondences in this setting, is that if I have a tangle cobordism, so what does this mean? It means that I have a surface sigma 1 and then another surface sigma 2. So this surface is punctured in some number of points. This surface is punctured in some number of points. And then there's a three-manifold cobordism from one surface to another with a tangle inside whose boundary are those punctured points. So that's what I call a tangle cobordism. And there could be a nearing on it as well. And the point is that to this, I can assign, I can apply the representation, traceless representation functor. And it turns out that what will happen is that the two representation spaces associated to surfaces are actually symplectic manifolds, could be singular symplectic manifolds. In fact, they are singular symplectic manifolds, but let's say smooth stratum possesses well-defined symplectic structure. And on that smooth stratum, the perturb traceless representation space associated to the inside, to the cobordism itself, right? So the complement of a tangle. So the perturbed one will be a Lagrangian correspondence on the smooth part, at least. So that's why we care about Lagrangian correspondence, because that's the notion that we get if we apply representation theoretic functor to cobordisms. Okay. And all right, well, so it's a Lagrangian inside the product of this times this, but the good part, the cool part is that we can also compose them. So the question would be, okay, if I have another cobordism, you know, how the two Lagrangian correspondences relate. How do I compose them? Yes, are there any questions? Is there any question? Oh, no. Okay. So yeah, now I want to describe this kind of the composition of Lagrangian correspondences, or rather, I will only need a case where one of the Lagrangian correspondences is just a simple Lagrangian. So the point is that if I have a Lagrangian correspondence from one manifold to another symplectic manifold, what happens is that I have a natural way to transfer Lagrangians in one manifold to Lagrangians in another manifold. And so intuitively, what happens, so if this is a Lagrangian in M1, and this is Lagrangian correspondence from M1 to M2, intuitively what happens is you kind of want to, you know, take L, project it into M1, then take the pre-image and then project it one more time into M2. And that's how this transfer works, at least on the intuitive side. Okay, but if we want to rigorously define it, the way to do it basically is to define a composition of Lagrangian correspondences. So if I have Lagrangian correspondence L01 from M0 to M1 and L12 from M1 to M2, there is actually a composition of them which will be a correspondence from M0 to M2. And the way one defines is just using the fiber product construction. So it's pairs of points here and here which map into the same point here. And it turns out that this is also an immersed Lagrangian inside the product of M0, M2 if certain transversality assumption is met. So there is a transversality assumption which needs to be met in order for this to be well defined. Okay, so that's how, and you know, this here, so this L is precisely the composition, I guess this is L prime, this is L composed with L10. It's a composition of this correspondence with this correspondence, except that this correspondence is just a Lagrangian. Okay, and so now finally, let me tell you why I introduced these objects. It's because adding an earring essentially amounts to composing with certain Lagrangian correspondence on the representation space side. Okay, so here's the picture. Okay, and I start with a tangle T, and okay, four-ended tangle. So the traces character variety of the four puncture sphere is going to be Pillowcase, and I call it P-in because it's the Pillowcase which is associated to the inside sphere. And so I've got a Lagrangian RT, the traceless representation space, mapping into the inside Pillowcase. But then what the adding an earring basically is the same as composing with this cobordism, right? So that means that this cobordism via representation functor outputs me some space V, which is, well, the representation space of the three manifold, which is sphere times an interval, and the inside tangle, which is just 4 points times an interval. And notice I'm putting natural here. That means that I added an earring here. Okay. And so this V, this representation space, well, it has a projection on the inside Pillowcase and on the outside Pillowcase, right? So these are the two projections. And so basically, if I want to construct R natural of T, what I ought to do is to compose with this representation variety of this cobordism. Okay, so the composition of RT with V, which, well, is a fiber product. So it's here. It's precisely the same representation space, but with added with an earring added. Okay, this is R of T composed with V. Okay, and so yeah, so this formula, I mean, right now it's kind of a general formula because we don't know what this space V is, right? But this is the formula which I want to unbundle in some way. So I want to describe you exactly what this V is, what this representation variety associated to this cobordism, and how it actually acts on all the curves, all possible curves. So we focus on studying this space. Yes. And let me now say that before I state the main result, that we actually, this space V is singular, unfortunately, but we can make it smooth if we perturb the right perturb it the right way. So here I drew this cobordism, which is again a two-sphere times an interval, right? And then, you know, these 4 strands inside, and then the earring. And then it turns out that we need to holonomy perturb around 2 curves. So one curve is this curve P, and another curve is this curve Q. Okay, and in the context of traceless, in the context of representation space, what it means to perturb is basically, it means that we need to work in the complement of these curves as well, but we need to also throw in 2 conditions, and these are the two technical conditions that we need to add to the whole representation space. So just to kind of reiterate all the conditions, it has to be traceless around the green parts. It has to be -1 around the blue arc. And then it has to be holonomy perturbed around P and then around Q as well. And so the conditions are that, you know, the values of the representations on the meridians of those curves are related to the values on the longitudes in this particular way. And you can see that if S is equal to 0, then representation has to be 1 on the meridian. So it's like I didn't really add those curves at all. So S equals 0 results in the unperturbed character variety. So, and Vs, and yeah, so there's a parameter here, S. So Vs is going to be a holonomy perturbed space where S is the perturbation parameter. And as I said, V0 is singular, but perturbed one is smooth, and I will describe the smooth one. Okay. So here's the main theorem of our work. The main theorem goes like this. So this is the picture that we need to have in mind. So there are 2 spheres, and then there's a cobordism between these 2 spheres with an earring. And so as a result, the representation space associated to this cobordism is Vs, and it projects into one pillowcase and into the other pillowcase. So first statement is that Vs is actually a smooth genus 3 surface for a generic small s parameter. And I drew it here. This is the genus 3 surface. But moreover, we can actually describe this map in this map. So the 2 maps into the pillowcases. And the two maps, they work as follows. Basically, if I take my genus 3 surface here and I decompose it into two parts, V plus and V minus, as described by cutting along this 4 belts, the map into this pillowcase can be described as just sending V plus. So V plus basically is a sphere without 4 disks, and I just send it bijectively into this P in the pillowcase with corners cut, essentially. So if I take this, and if I take this, right, these are really the same things. So I just bijectively send one to another. Okay. And V minus as well. And so you can see that the V minus and V plus, they are glued along these belts, right? So therefore, if I send V minus here and I send V plus here, the two maps glue along these belts on the pillowcase. Okay, so that's the first map. And then the interesting thing is that the other map is very similar. So it's actually the same map Rin, except that it is precomposed with Dane twists. So on this surface, there's 4 Dane twists that we can define: the Dane twist along C1, the Dane twist along C2, C3, and C4. So act by Dane twist along all those CIs, and then do the same map, and that's going to be the map R out. Okay, so that's basically the main results of our work, those involve kind of a lot of computations of this representation space VS and kind of certain reductions, or how should I say, one takes certain element, gauge fixes it by acting by SU2 so that that element is I, for example, and then considering all other elements. But yeah, but it's kind of much more complicated in this case. So yeah, so that's the same. Any questions about the statement of a theorem? All right, so let me proceed then. The point is that from the statement of this theorem, we can actually deduce the action on curves. So the action on curves, what do I mean by this? Well, I've got a Lagrangian correspondence into P in and P out. And let's say I have a curve inside the inside pillowcase. What is the image under this correspondence of this curve? And well, so this picture describes it. So if I start with the curve, with this curve, let me start with the blue one. So let me start with this curve. The pre-image of this curve inside my Lagrangian correspondence is going to be these 2 belts here. Well, okay, now I want to map to the outside pillowcase. In order to do that, I need to precompose with Dane twists. But the Dane twists don't really change these curves, right? Because the Dane twists are along these belts which don't intersect the blue part. So the blue curves stay the same. But there are 2 of them now, right? And then if I project these 2 belts into the outside sphere, outside pillowcase, I get exactly 2 copies of the same curve. So basically, the first point is that if I start with a compact curve, which does not go to corners, this correspondence actually doubles the compact curve. But the interesting thing happens for non-compact curves, right? Because if I have an arc like this, well, the pre-image inside my my Lagrangian correspondence V is going to look like this. And now the Dane twists actually act non-trivially on this curve, right? So if I act by Dane twists, what I'm getting is the same curve, but now with this twist, right? And now if I project to the outside pillowcase, it turns out that, so these two parts, they just contribute 2 copies of the same curve, right? But these 2 Dane twists essentially result into this kind of half circles around the corners. And so as a result, if I start with an arc on my pillowcase, the result is a figure 8 based on that arc. So yeah, and yeah, so that's the action on these curves. And let me maybe say one also remark on the proof. So yeah, but yeah, so basically this follows from this description, right? I just kind of wanted to explain, because this was the main goal, is to understand how the curves translate via this Lagrangian correspondence. And then let me maybe say a remark on the proof of why this VS is really genus 3 surface. And the way it kind of works is the following. So first, one wants to compute V0, the singular space which is not perturbed, the unperturbed one. And it turns out that that singular space has a well-defined kind of map onto the pillowcase, such that the regular fiber of this map is S1, whereas over the corners is just 1 point. And so as a result, this space is a 3-manifold and has kind of this 4 singularities here. And then if one tracks what happens using the perturbation, it turns out that each fiber, you kind of perturb it using some Morse function on this fiber, and so the fiber becomes 2 points instead of a circle. And so generically, for each point on this pillowcase, we'll get 2 points in the perturbed representation space. And so the V0 essentially perturbs into one pillowcase, which is here, and then the kind of the outside pillowcase. But the interesting part is that along the on the corners, the fiber was just 1 point, but once one perturbs, you know, these 2 pillowcases basically glue along the circles here. Okay, and so this is how essentially one gets the genus 3 surface. Okay, and I mean, of course, it's very hard to prove the exactly how they glue. Instead, we kind of argued by topology, and the key fact was that this VS, the representation space, the Lagrangian correspondence misses the corners, right? So in this statement, actually, I didn't stress it, but this was actually super important, that when I map this space to one pillowcase or the other pillowcase, these corners, the singular corners, are not touched. They're not in the image. That's really the most important fact, because once one has that, everything else kind of falls from the topology and differential topology. Yeah, and also this, yeah, it's nice because, I mean, if it would map into a corner, then we wouldn't really be able to define a Lagrangian correspondence. But since it doesn't map into a singular part, it does define a Lagrangian correspondence between 2, I guess, open pillowcases. Okay. Yeah, so this was the statement of results, essentially, a couple of remarks about the proof. And now I want to talk a little bit about the kind of the implications of this. So what So first, basically, an answer to Danny's question is, in the case of trefoil, what do all these results tell us? Well, they tell us that in the case of trefoil in particular, if I, consider my knot without any earring, then I have this arc and this arc. Now, if I put an earring on the red part, well, this arc will become a figure 8. If I put an earring on the blue part, then this arc will become a figure 8. And so in both cases, the Floer homology is 3-dimensional. And it looks like in this case, there's no dependence on the earring location. The two Floer homologies are isomorphic. And just to stress what's going on, essentially, we've got this R and then the red representation space, the blue representation, and then there's in between this representation space V. And I can compose the red part with V and intersect here, or I can compose the blue part with V and intersect here. And this is what's really going on. Perhaps, yeah.
So Artem, I know, just to follow up a bit. So this is a case, of course, where you're saying, in some sense, you can see visually that there should be no differential. So you're saying, the chain complexes are the same. So for instance, in this example, if you had, you could sort of maybe artificially build a little differential by maybe taking this the middle picture at the bottom and just doing some perturbation that puts it like essentially do a little finger move that makes something like that. So I guess I was thinking it like in the picture in the middle, on the one side that would then double to get it. So I was imagining that you actually did this in the
in the middle. I'm sorry.
In the middle, and then it somehow affects both sides. So if you put that little extra intersections, something like this. So I'm just trying to think through what happens. So I guess when you then go to the left, you're going to build that, you're going to kind of double up that. And am I supposed to be able to see like the differentials that are sort of?
Yeah, let's do it. Actually, I didn't do this particular one, so we could definitely do it. So in this case,
yeah, I think you could do it. Yeah. That's easier than trying to move the blue ones.
Yeah. So in this case, so basically you've got a bunch. You've got
you have that. So is it somehow that quadrilateral? I guess in that picture is somehow acyclic. Is that the point?
Yeah. So the point is that basically. So let me. So first of all, there's this bygone.
Oh, I see. And then the other.
And then there's this bygone, and then there's also this bygone. So once you kind of do this finger moves, which kind of cancel this bygone. So I guess, yeah.
So I see. So you're just saying this is somehow part of the basic theory that one would expect. I know it's not proved in general, but one would expect.
Yeah. Basically, the bygones will take care of the fact that it's 6-dimensional, but it needs to be 3. It needs to
I don't mean.
Sorry, it's 7-dimensional, but it needs to be 3-dimensional. Yeah.
And then something similar is going to happen on the other side.
Exactly. Yeah.
Oh, okay. Thanks. That's interesting.
Sure. Yeah. And actually, if you play around and do something like this, like in the middle of the picture, it always works out. But it turns out that if you do something more interesting on the corner, then it doesn't. And that was kind of the part of the kind of a little bit unexpected in some sense result of this is that in the 4-5 torus knot, and the way we imagine 4-5 torus knot is take this unknot, take this Conway sphere and do 3-4 surgery along this curve and 5-4 surgery along this curve. And this will result into 4-5 torus knot. And it turns out that then, this is a trivial tangle. So for the trivial tangle, I know precisely what's going on. It's an arc So, you know, without an earring and with an earring, it's going to be a figure 8. Now, the other part, the red part, right, corresponding to this kind of super complicated tangle is much more complicated. And so Harold, Hedden, and Kirk, they computed precisely what's going on there. And the result is basically that without an earring, it looks like this. So it's an arc. It's kind of fairly complicated, but it's the red arc on this diagram. Okay. So what's interesting about this picture is that if you place an earring on the blue part, there's going to be one bygone in the picture. And so there's going to be like a 9-dimensional intersection with one bygone, which will result in 7-dimensional Floer homology. And 7-dimensional Floer homology is precisely instanton Floer homology of 4-5 torus nodes. So that's great. But the unfortunate part is that if we do the same thing, but place an earring on the red part, what happens is that, I don't know, it's kind of complicated. So you don't have to follow it, you know, how this red curve translates into this red curve. But let me say the punchline is that there's 9 intersections and there are no bygones at all. And so here it's 9-dimensional and it's not singular instanton homology. So this is in some sense a counterexample to pillowcase homology construction. And for a long time, we didn't understand what's going on. Like if we have a bygone here, why does it disappear here? And so now, having studied this Lagrangian correspondence, we now understand where that bygone kind of disappears. So let me explain this to you. So now localizing the picture, right? I mean, this is kind of complicated. We don't care about most of these intersections. We care about the following kind of localized picture. So this is one corner, a neighborhood of one corner, basically. And the point is that on one side, I'm turning my blue into figure 8, and my red looked like this, and I have this bygone from this intersection to this intersection. Whereas in the other picture, if I don't turn my blue into a figure 8, so it's just an arc, but rather my red part gets doubled, right? So I just draw a double, because that's what our theorem tells us. We've got 4 intersection points and no bygones between them. So that's the kind of the crux of the problem. And the question is, well, okay, in this localized picture now, why the differential disappears? So this was kind of the second part of our project, is to understand this phenomenon. And kind of the philosophical answer, which I want to first state, is that the action which I described by VS, which doubles compact arcs and turns non-compact to figure 8s, actually does not induce a well-defined functor on the Fukaya categories. And I mean, one can view it in different ways, and kind of, and I will elaborate on this. But the answer is that there must be a bounding cochain added. And just for the sake of concreteness, bounding cochain is a self-intersection of a curve, essentially. And so in this case, this bounding cochain must be added. And the point is that once you add this bounding cochain in the right way, and I'll explain exactly how one has to do it, then counting polygons with corners on that bounding cochain has to resolve the problem. And so the point is that in this case, there's a triangle here with a corner on this bounding cochain, which goes precisely from this intersection point to this intersection point. And this triangle is precisely the kind of the thing which should correspond to this bygone. Okay, so that's kind of the answer, but of course, it's not a satisfactory answer because I didn't tell you how this bounding cochain, like why do we need to add this self-intersection B, and why do we need to count exactly the triangles to recover that bygone? So let me kind of motivate this a little bit now. And so in order to do this, I need to consider quilted Floer homology. So quilted Floer homology is a construction due to Warheim and Woodward. And yeah, is there a question?
It's going to be, it starts at 3:30, it's going to be short.
All right. So yeah, it's quilted Floer homology is a homology theory which is associated to a sequence of Lagrangian correspondence. So basically the input is now two pillowcases, Lagrangian correspondence from one pillowcase to another, and two Lagrangians, R2 and R1. So that's the whole input, okay? And the construction basically counts certain objects called quilts. So we count a strip, a bygone inside one pillowcase, and a bygone in the other pillowcase. And then there are boundary conditions. So this boundary has to go into one Lagrangian, this boundary has to go to another Lagrangian. And then there's a seam. So along the seam, we need to glue two strips, and the seam should go to Lagrangian correspondence. And the two strips have to glue to each other. So yeah, this is kind of an informal definition, but counting this kind of objects defines quilted Floer homology. And the point is that quilted Floer homology by construction, it recovers both the Floer homology of RT1 and RT2 with an earring, but also the other one, so RT2 and RT1 with an earring. So I can consider Floer homology here or here. This was dependence on the earring, right? Or I can consider the whole quilted Floer homology. And the point is that the quilted Floer homology is defined in such a way that it is actually isomorphic to both this and this, with one caveat, that this is true only if everything is embedded. But in our case, unfortunately, everything's immersed, right? And so problems occur in this construction. So basically the problems occur in the proof that Floer homology is actually the same as this and this. And the answer which Botman and Warheim figured out is that, yes, there is a problem, but there's a remedy to that problem. There's a recipe to solve that, and the recipe is to count certain degenerations called figure-8 bubbles, and those precisely produce bounding cochains B, which resolve this problem. And so let's now illustrate this phenomenon. I'm over time, unfortunately, but yeah, let me just, I guess, let me illustrate it here. So the idea is that once you have this quilt, you take one strip and the kind of the width of it, and take the other strip and the width of it. And if you limit this width to 0, you'll obtain the bygone that we kind of started with. So this bygone is obtained when one epsilon goes to 0. So kind of in strip shrinking on one side. But what happens if we shrink this strip? So that's the content of Botman and Warheim, I guess, theorem / conjecture. And it turns out that in this case, what will happen is, you see this strip, right? The width of it degenerates into 0, this epsilon 2. But then it turns out there's this phenomena. There could be a phenomena like this occurring, where such a quilt degenerates into a triangle and then a figure-8 bubble. So if we count these figure-8 bubbles, we precisely recover the bounding cochain. Yeah, sorry for rushing through the end, but yeah, basically there's this counting of these figure-8 bubbles allows to recover this bounding cochain. And what we did is we recovered the homotopy class of the bounding cochain bubble. We were not quite able to pin down the pseudo-holomorphic representative of this figure-8 bubble, but we kind of conjecture that it must be there in order for the differential to be revived, essentially. So that's it. Thank you.
Awesome. Are there questions?
Hi, Artem. Thanks for the talk. I have a question, which might I have asked you before, but I don't remember. So if you don't add any earring, presumably you should be able to recover the S1 equivariant structure, some additional structure in the form of S1 equivariant homology. Do you understand from the Pillowcase picture how it would show up?
Yeah, I think yeah, I don't know for sure, but I would definitely expect basically a wrapped behavior. So for example, in this case, if we, I would consider wrapped Floer homology. And so as a result, you know, we'll have a tower of generators here and one generator here. And so, you know, this S1 equivariant instanton homology of right-handed trefoil. I'm not 100% sure, but I think it should be something like this, right? And so
Right.
this tower is precisely comes from the wrapping behavior, I think.
I see. So that tower is it's coming from the reducible solution.
Yes, yes, precisely, right? Because yeah, before I wrapped, these two things, you know, met at the reducible point. So yeah.
How do you see the ring structure?
The module structure, you mean?
Yes, the modular structure.
Yeah. Yeah, so it is possible to see the module structure, but yeah, it's fairly complicated, I think. But yeah, it depends. So there are two viewpoints actually. So in this viewpoint, I believe it's possible, and essentially the answer is, so let me maybe zoom in. So let me erase this. So so there's two possibilities. So let's have the first possibility, which is just to take a wrapped Floer homology. And in this case, I think the module structure should come from snails, essentially. So for example, it's an index 2 disk which goes over the corner of the pillowcase. So if this is like 1, this should be X, and this kind of snail, counting snails essentially should recover the module structure. Yeah, but also there's a different possibility, because here I'm taking wrapped Floer homology, but one could also actually work in the torus. So torus kind of that branch covers pillowcase, and so one can take the lifts of R and take Z2 equivariant Floer homology of these two things, and actually the dimension-wise the answer will be the same, but the module structure will be lost. So yeah, so that's kind of a different approach to the same to recovering this S1 equivariant instanton homology. So the first one is wrapped. And the second one is basically Z2 equivariant Floer inside the torus. And the module structure here is snails, but if we do the second way, which is Z2 equivariant in the torus, I don't know how to recover the module structure. Actually, there is a module structure, but it's the wrong one. So there's a module structure, but yeah, it doesn't recover what we want.
Right. Okay, thank you.
Yeah, absolutely.
I should also mention we'll be back in an hour, week minus an hour with Cliff Taubes talking about eigenvalue problems on the two-sphere. Can file further questions.
Artem, can you go back to the picture where the problem occurs? Yeah, and it actually then.
This one?
Yeah, that one. Yeah, I just want to look at that some more. Okay, I've looked at it some more. That's great. Thanks.
Yeah, absolutely.
Hi, Artem. So can you read off the local coefficient structure that Kronheimer and Ravka use in many of their papers from the pillowcase picture?
Well, that I don't know, to be honest. Yeah, I mean, it might be, yeah, probably has to do with the corners, but yeah, I really don't know.
Another question is, so for I sharp, I imagine it was a similar story, but where you just kind of have a Lagrangian correspondence, which involves just putting a half link kind of away.
Yeah.
Is that, I mean, do you know what that looks like in the end, or is it interesting?
Yes. Let me remember. Yeah, I think we didn't work out what the VS, the Lagrangian correspondence for this, but I remember that, I mean, if let's say in the trefoil case, for example, if one would add, instead of an earring here, one would add a hop link, right? Then what will happen is that instead of one figure eight, there will be actually 3 figure eights. If I'm right. No, maybe there should be 2 figure eights.
Yeah.
Probably 2 figure eights, yes.
2 figure eights.
Yeah. So, yeah, my kind of guess would be that probably everything's doubled. So the Lagrangian correspondence might be also doubled from this picture, but I'm not 100% sure what didn't compute it. Yeah, maybe since I rushed through the end, let me just maybe add that, yeah, one can kind of, if one stares enough into this kind of picture, the point is that here or which picture? Yeah, this picture. Here I drew the quilt which corresponds to this, the quilt which corresponds to the bygone. And so you can kind of see this bygone here, right? And so the way to come up with a quilt is that, well, just take this boundary a little bit off So this will be the seam. And then, you know, okay, this picture is is really complicated, but the seam goes, you know, here in the Lagrangian correspondence, and then the corresponding kind of leftover, which goes into the outside pillowcase, looks something like this. So this is, if we start with the bygone and then we try to kind of understand what the quilt is, well, it's going to be the same bygone, except here we kind of moved this boundary a little bit. And so the leftover on the outside pillowcase will look like this. And so the question now, okay, what if now I push this boundary into the red part? What actually happens with this leftover on the outside pillowcase? And it turns out that this leftover picture, and this is what Botman and Waheim tell us, is that actually it has to degenerate into this blob, this figure-8 bubble, and then triangle here. And so really this kind of, this bygone, which we started with, kind of on the other end of the moduli space corresponds to this triangle together with this figure-8 bubble. And so notice that if I count these figure-8 bubbles, well, I will recover this bounding cochain B. And so as such, I will be able to recover this triangle here. So yeah, this is kind of the last 2 minutes that I wanted to add. But yeah, thanks a lot for coming and listening to me.
Well, maybe we should just thank Artem again for a great talk. So.